What if the planet keeping you alive right now is also the one that once nearly wiped out all life? On Earth, Jupiter is not what you think it is. Most people glance up at the night sky, see a bright dot near the horizon, and never give it a second thought. But that bright dot is the single most important object in our solar system after the sun itself. And there is a credible scientific argument that without it, you would not exist. Your species would not exist, and the Earth might be nothing more than a cratered, lifeless rock drifting through space. Jupiter is the largest planet in our solar system. A colossus of swirling gas and liquid so massive that it warps the trajectories of everything around it. From tiny pebbles of space debris to full-blown comets screaming through the void at tens of thousands of miles per hour. Its gravitational influence is so profound that it literally tugs on the sun itself, causing our parent star to wobble ever so slightly in its position. A fact that astronomers have confirmed through decades of precise measurement. The center of mass between Jupiter and the Sun does not actually sit inside the Sun. It sits just above the solar surface, roughly 30,000 miles outside the Sun's photosphere, making Jupiter the only planet in our solar system heavy enough to pull off that feat. And yet, despite all of this, despite its incomprehensible size, its planet-shattering gravity, and its role as the architect of our solar system's current layout, most people know almost nothing about Jupiter beyond the fact that it is big and has a red spot. That is about to change. Over the course of this piece, we are going to dismantle everything you thought you knew about this gas giant and reconstruct a picture of Jupiter that is far stranger, far more violent, and far more consequential to your personal existence than you have ever imagined. We're going to talk about what is actually happening inside Jupiter right now, where pressures are so extreme that hydrogen, the lightest and simplest element in the universe, transforms into a liquid metal that conducts electricity better than copper. We're going to talk about storms so large they could swallow the entire Earth 3 times over, and so persistent they have been raging without interruption for more than 3 centuries. We are going to talk about moons that harbor oceans bigger than all of Earth's water combined. Oceans that might, at this very moment, contain living organisms. And we are going to confront the stunning fact that Jupiter very nearly became a second sun in our sky, and what that would have meant for every living thing on this planet. Let us start with the basics, but not the basics you learned in school. Jupiter's diameter measures approximately 86,881 miles, which is roughly 11.2 times the diameter of Earth. If you could hollow Jupiter out like a pumpkin, you could fit more than 1,300 Earths inside it. That number alone should make you pause and reconsider the scale of what we are dealing with. But the diameter is not even the most impressive statistic. Jupiter's mass is approximately 4.185 times 10 to the 27th power pounds, which works out to roughly 318 times the mass of Earth. To put that in perspective, if you took every other planet in our solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and combined all of their masses together, Jupiter would still outweigh the lot of them by a factor of about 2.5. Jupiter alone accounts for approximately 70% of all planetary mass in our solar system. It is not just the biggest planet, it is bigger than everything else combined, and then some. This staggering mass is the source of Jupiter's gravitational dominance. And that gravitational dominance is the reason Jupiter has played such an outsized role in shaping the history of our solar system and, by extension, the history of life on Earth. Now here is where things get strange. Jupiter has no surface. There is no ground, no solid crust, no rocky terrain where a spacecraft could land. If you were to descend into Jupiter's atmosphere in some impossibly durable vehicle, you would pass through layers of ammonia ice clouds, then ammonium hydrosulfide clouds, then water ice clouds, and then things would just keep getting denser and hotter without any clear boundary between atmosphere and something else. The planet is composed primarily of hydrogen and helium, roughly 90% hydrogen and 10% helium by number of molecules, which is remarkably similar to the composition of the Sun. As you descend deeper, the pressure increases relentlessly. At about 600 miles below the cloud tops, the pressure reaches a point where hydrogen gas smoothly transitions into liquid hydrogen without a distinct boiling point. a phenomenon that occurs because the temperature and pressure exceed what physicists call the critical point of hydrogen. There is no surface of a hydrogen ocean the way there is a surface of the Pacific Ocean. The gas simply becomes denser and denser until it behaves as a liquid. This liquid hydrogen ocean is the largest ocean in our solar system by a staggering margin, extending tens of thousands of miles deep into Jupiter's interior. But the real insanity begins even further down. At roughly 12,000 to 15,000 miles beneath the cloud tops, the pressure exceeds approximately 2 million atmospheres, which is about 2 million times the air pressure at sea level on Earth. At these pressures, hydrogen molecules are squeezed so tightly together that the electrons are stripped from their atoms and become free to move, turning hydrogen into a metallic substance that conducts electricity just like a metal. This is metallic hydrogen, a state of matter so extreme that scientists on Earth have only been able to produce it in fleeting, microscopic quantities using diamond anvil cells and laser shock compression experiments. Inside Jupiter, metallic hydrogen exists in a layer that is estimated to be tens of thousands of miles thick and contains a significant fraction of the planet's total mass. This metallic hydrogen layer is critically important because it is the engine that drives Jupiter's magnetic field, the most powerful planetary magnetic field in our solar system. And we will return to that magnetic field shortly because it is one of the most jaw-dropping features of this planet. At the very center of Jupiter, scientists have long debated what exists. For decades, the two leading hypotheses were that Jupiter either has a dense rocky core roughly 10 to 20 times the mass of Earth, composed of rock, metal, and ice that served as the seed around which the planet originally formed, or that it has no distinct core at all and hydrogen simply continues all the way to the center under increasingly absurd pressures. The answer, it turns out, is neither of those simple options. NASA's Juno spacecraft, which arrived at Jupiter on July 4, 2016, and has been orbiting the planet in highly elliptical polar orbits ever since, has provided the most detailed gravitational measurements of Jupiter's interior ever obtained. By tracking the precise Doppler shifts in Juno's radio signal as the spacecraft passes close to Jupiter, scientists can map tiny variations in the planet's gravitational field, which in turn reveal how mass is distributed inside the planet. The Juno gravity data, published in a landmark 2022 paper in the journal Nature, revealed something unexpected. Jupiter does have a concentration of heavy elements at its center, but this core is not a neat, compact ball of rock. Instead, it is what scientists call a dilute core or fuzzy core, a region extending out to roughly 30 to 50% of Jupiter's radius where heavy elements such as rock, metal, and ice are mixed in with hydrogen and helium at gradually decreasing concentrations. There is no sharp boundary between the core and the overlying metallic hydrogen. The heavy elements are smeared out over a vast volume. This fuzzy core is a major clue about Jupiter's violent past. One leading explanation is that Jupiter originally formed with a compact rocky core, but sometime during the first few 100 million years of the solar system's existence, another large protoplanet, perhaps 10 times the mass of Earth, slammed into Jupiter at tremendous speed. This giant impact would have had enough energy to shatter and disperse the original core, mixing its heavy elements into the surrounding hydrogen and helium layers and creating the dilute, spread-out core structure that Juno observes today. Computer simulations published by a team led by Shangfei Liu at Sun Yat-sen University in 2019 showed that a head-on collision with a protoplanet roughly 10 Earth masses could reproduce the observed fuzzy core structure remarkably well. If this scenario is correct, it means that even a planet as enormous as Jupiter was not immune to the violent collisions that characterized the early solar system, and its current internal structure bears the scars of an ancient cataclysm. The temperature at Jupiter's core is estimated to be roughly 43,000 degrees Fahrenheit, which is hotter than the surface of the Sun, though far cooler than the Sun's core. The pressure at the center is estimated at approximately 50 to 100 million atmospheres. Under these conditions, the behavior of matter is so extreme that it pushes the boundaries of our current understanding of physics. No human-made object could survive even a tiny fraction of the journey to Jupiter's center. The deepest any probe has ever penetrated into Jupiter's atmosphere was achieved by the Galileo Atmospheric Entry Probe on December 7, 1995. That probe descended through Jupiter's cloud layers for 57.6 minutes, reaching a depth of approximately 95 miles below the cloud tops before the combination of extreme temperature, roughly 305 degrees Fahrenheit, and pressure, about 23 atmospheres, destroyed the probe and cut off communication. 95 miles. Jupiter's radius is approximately 43,441 miles. The Galileo probe barely scratched the surface, or rather, barely scratched the top of an atmosphere that has no surface, before being crushed. Everything we know about what lies deeper comes from remote sensing, gravitational measurements, and theoretical models. Jupiter's interior remains one of the last great unexplored frontiers in our solar system. Now let us talk about the storms, because they are the feature that most people associate with Jupiter, and yet most people drastically underestimate just how extreme they are. The Great Red Spot is the most famous storm in the solar system. A colossal anticyclonic vortex, meaning it is a high-pressure system with winds circulating counterclockwise in the southern hemisphere, that has been continuously observed since at least the late 1600s. The astronomer Giovanni Cassini is generally credited with recording it in 1665, though there is debate about whether the spot he observed is the same one we see today or a predecessor. Regardless, the current Great Red Spot has been monitored continuously since at least the 1830s, making it a storm that has persisted for a minimum of 190 years and potentially much longer. The storm's dimensions are staggering. At its peak in the late 1800s, the Great Red Spot was estimated to be roughly 25,000 miles across in the east-west direction, large enough to fit about 3 Earths side by side within it. In the north-south direction, it spans roughly 1 Earth diameter, approximately 8,000 miles. However, the storm has been shrinking. Observations over the past century and a half show a steady decrease in the east-west dimension. And by the 2020s, the storm had contracted to approximately 10,000 miles across, about 40% of its historical maximum. Whether this trend will continue until the Great Red Spot eventually disappears entirely is one of the open questions in planetary science. Some researchers believe the storm could vanish within the next few decades. Others argue that internal dynamics might stabilize it at a smaller size. What makes the Great Red Spot so remarkable is not just its size, but its longevity. On Earth, even the most powerful hurricanes last a few weeks at most before they lose energy and dissipate. The Great Red Spot has lasted centuries. The reason is fundamentally different energetics. Earth's hurricanes draw their energy from warm ocean water and lose it when they move over land or cooler water. The Great Red Spot draws its energy from Jupiter's internal heat and the massive temperature gradients in the planet's atmosphere, both of which are essentially inexhaustible on human timescales. Jupiter radiates approximately 1.67 times more energy than it receives from the Sun, meaning the planet has a substantial internal heat source, the slow gravitational contraction left over from its formation, that continuously drives atmospheric convection and feeds the storm systems. Wind speeds within the Great Red Spot reach approximately 270 miles per hour at the outer edges, with complex internal circulation patterns that have been mapped in detail by spacecraft from Voyager to Juno. For comparison, the strongest Category 5 hurricane ever recorded on Earth, Hurricane Patricia in 2015, had peak sustained winds of approximately 215 miles per hour. The Great Red Spot's winds comfortably exceed this, and they have been doing so for centuries without pause. But the Great Red Spot is far from the only storm on Jupiter. The entire planet is covered in bands of alternating light and dark coloration. The bright bands are called zones and the dark bands are called belts, and each boundary between a zone and a belt features a powerful jet stream with wind speeds that can exceed 400 miles per hour. Jupiter's rapid rotation is the driving force behind this banded structure. Despite being the largest planet in the solar system, Jupiter has the shortest day. It completes one full rotation on its axis in approximately 9 hours and 56 minutes. This extremely rapid spin, remember, Jupiter's equator is moving at roughly 28 0.000 miles per hour compared to Earth's equatorial rotation speed of about 1.040 miles per hour, generates immense Coriolis forces that organize the atmospheric circulation into those characteristic east-west bands. The Juno spacecraft's gravity measurements revealed that these jet streams are not merely a superficial phenomenon confined to the top few miles of atmosphere. They extend down to a depth of approximately 1,860 miles, far deeper than anyone expected. Below that depth, the increasing electrical conductivity of the hydrogen, as it transitions toward metallic hydrogen, causes magnetic braking that suppresses the differential rotation and forces the deeper interior to rotate as a rigid body. This means the colorful banded structure we see on Jupiter's surface is the visible manifestation of atmospheric currents that reach thousands of miles deep, making Jupiter's weather system a fundamentally three-dimensional phenomenon that dwarfs anything in our terrestrial experience. At Jupiter's poles, the atmospheric dynamics become even more bizarre. The Juno spacecraft, which passes over the poles on each orbit, captured the first detailed images of Jupiter's polar regions, and what it found astonished scientists. At the North Pole, there is a central cyclone surrounded by 8 smaller cyclones arranged in a remarkably stable octagonal pattern. At the South Pole, there is a central cyclone surrounded by 5 cyclones in a pentagonal arrangement. Each of these individual cyclones is roughly 500 to 500 miles in diameter, comparable in size to the entire continental United States, with wind speeds reaching up to 225 miles per hour. These cyclones have maintained their geometric configurations for the entire duration of Juno's mission, raising profound questions about what physical mechanisms prevent them from merging into a single large vortex or drifting apart. Research published in the journal Nature Physics in 2022 suggested that an anticyclonic ring, a band of winds flowing in the opposite direction, around each polar cyclone cluster acts as a shield that keeps the individual storms separated and stable. This is a phenomenon that has no counterpart on Earth and represents a genuinely new type of atmospheric dynamics that was unknown before Juno. Then there is the lightning. Where there are storms, there is lightning, and Jupiter delivers on that front with characteristic excess. The Voyager 1 spacecraft first detected lightning on Jupiter's night side in 1979 as bright flashes in the clouds. Subsequent missions confirmed that Jupiter produces lightning primarily in its deep water clouds, where the mechanism is thought to be similar to Earth's. The collision and separation of ice particles in convective updrafts generates electrical charge separation that eventually discharges as lightning. However, Juno discovered something additional and surprising. Using its microwave radiometer, Juno detected shallow lightning originating from clouds at higher altitudes where the temperature is too cold for pure liquid water to exist. The proposed explanation, published in Nature in 2020, is that a mixture of water and ammonia, essentially an ammonia-water slush, can remain liquid at much lower temperatures than pure water, and collisions of these slush particles generate the observed shallow lightning. The energy of individual Jovian lightning strokes has been estimated to be hundreds of times greater than typical terrestrial lightning, with some superbolt discharges releasing energy comparable to Earth's most powerful lightning events. Juno also detected evidence of transient luminous events in Jupiter's upper atmosphere, phenomena analogous to the sprites and elves that occur above thunderstorms on Earth, confirming that Jupiter's electrical activity extends from deep in the water cloud layer all the way up to the stratosphere, spanning a vertical range of hundreds of miles. If you could somehow hover in a spacecraft within Jupiter's cloud layers, setting aside the fact that you would be crushed, baked, and torn apart by winds, you would witness a landscape of towering cloud formations lit by continuous flashes of lightning of almost unimaginable power. The deep rumble of thunder conducted through an atmosphere dense enough to transmit sound with terrifying efficiency, and the endless howl of winds moving at speeds that on Earth would qualify as weak tornadoes even in the calmest regions. In 2021, observations made with the Atacama Large Millimeter Array, known as ALMA, a powerful radio telescope array in Chile's Atacama Desert, revealed that wind speeds in Jupiter's stratosphere, the layer of atmosphere above the main cloud tops, reach approximately 900 miles per hour near the poles. This is roughly the speed of sound in air at sea level on Earth, making these among the fastest atmospheric winds ever measured on any planet. The stratospheric winds are particularly remarkable because they exist in a region of the atmosphere that is above the main weather layer, suggesting that they are driven by different mechanisms than the tropospheric jet streams, possibly by energy deposition from auroral processes at the poles, or by the upward propagation of atmospheric waves from below. Let us now turn to one of the most fascinating aspects of Jupiter, its role as the guardian and occasional executioner of the inner solar system. Jupiter's immense gravity acts as a kind of cosmic vacuum cleaner, sweeping up or deflecting many of the comets and asteroids that would otherwise pose a threat to Earth. The idea that Jupiter serves as a protective shield for Earth has been a prominent concept in planetary science since the 1990s, and it gained dramatic public attention in July 1994, when a fragmented comet called Shoemaker-Levy 9 slammed into Jupiter in one of the most spectacular astronomical events ever witnessed. Shoemaker-Levy 9 had been captured by Jupiter's gravity during a close approach in 1992 and was torn apart by tidal forces into at least 21 major fragments arranged in a line. Astronomers informally called them the String of Pearls. Over the course of 6 days, from July 16th to July 22nd, 1994, these fragments plunged into Jupiter's atmosphere one by one, creating a series of enormous fireballs and leaving dark impact scars in the clouds that were visible from Earth through amateur telescopes. Some of the impact scars were larger than Earth itself. The largest fragment, designated Fragment G, struck Jupiter with an estimated energy of approximately 6 million megatons of TNT, roughly 600 times the combined yield of all nuclear weapons on Earth. NASA scientists estimated that if a similar comet had struck Earth instead, it would have triggered a mass extinction event comparable to the Chicxulub impact that wiped out the non-avian dinosaurs 66 million years ago. The Shoemaker-Levy 9 impact was a visceral demonstration of Jupiter's role as the solar system's catcher's mitt, absorbing an impact that could have been catastrophic for life on Earth. Jupiter's impact rate is staggering compared to Earth's. Estimates suggest that Jupiter is struck by objects roughly 2,000 times more frequently than Earth, owing to its enormous cross-section and powerful gravitational focusing effect. Objects of about 30 feet in diameter, large enough to produce a significant atmospheric explosion on Earth, like the 2013 Chelyabinsk meteor that injured over 1,500 people in Russia, strike Jupiter dozens of times per year. The same class of object hits Earth only once every several years to once every couple of decades. Amateur astronomers have captured multiple Jupiter impacts on video since the Shoemaker-Levy 9 event, including notable flashes observed in 2009, 2010, 2012, and 2019, confirming that Jupiter is continually absorbing objects from the solar system's debris population. However, the story is not quite as simple as Jupiter protects Earth. Some researchers have argued that Jupiter is actually a double-edged sword, a guardian that also creates threats. Jupiter's gravity can deflect objects away from Earth, but it can also deflect objects toward Earth by perturbing the orbits of comets and asteroids in ways that send them into the inner solar system. A 2008 study by Jonathan Horner and Barry Jones at the Open University in the United Kingdom used computer simulations to investigate what would happen to the impact rate on Earth if Jupiter were different sizes or did not exist at all. Their results were nuanced. They found that removing Jupiter entirely actually decreased the impact rate from some populations of objects, such as those originating in the asteroid belt, while increasing it from others, particularly short-period comets originating from the outer solar system. The net effect depended on which population of impactors was considered. In some scenarios, a Jupiter-free solar system actually experienced fewer catastrophic impacts on Earth than our real solar system does. This suggests that calling Jupiter Earth's shield is an oversimplification. Jupiter is more accurately described as a gravitational traffic cop. It redirects the orbits of small bodies in complex ways, sometimes steering them away from Earth and sometimes steering them toward it. The net balance of these effects is still a matter of active scientific debate. There is even a provocative hypothesis that Jupiter may have been responsible for the very impact that killed the dinosaurs. The Chicxulub impactor, the roughly 6-mile-wide object that struck what is now the Yucatan Peninsula approximately 66 million years ago and triggered the Cretaceous-Paleogene extinction, was long assumed to be an asteroid from the main belt between Mars and Jupiter. However, a 2021 study by Amir Siraj and Avi Loeb at Harvard University proposed that the Chicxulub impactor may have actually been a fragment of a long-period comet that was deflected into a sun-grazing orbit by Jupiter's gravity. In their model, Jupiter's gravitational influence occasionally sends long-period comets from the outer solar system onto trajectories that pass extremely close to the Sun, where tidal forces break them apart into smaller fragments, some of which then cross Earth's orbit. If this hypothesis is correct, and it remains controversial, then Jupiter's gravity may have indirectly caused the most famous mass extinction in Earth's history, even as it presumably prevented many other potential impacts. The relationship between Jupiter and the origin of life on Earth extends far beyond just the impact. Question: Jupiter played a foundational role in shaping the architecture of the entire inner solar system during the first few hundred million years after the Sun's formation. The leading model for this process is called the Grand Tack hypothesis, first proposed by Kevin Walsh, Alessandro Morbidelli, and colleagues in 2011. In this model, Jupiter formed quickly in the outer solar system, roughly 3 to 4 times Earth's distance from the Sun, and then migrated inward toward the Sun due to interactions with the disk of gas and dust that still surrounded the young star. Jupiter's inward migration took it as close as about 1.5 astronomical units from the Sun, roughly where Mars orbits today, where it encountered Saturn, which was also migrating inward, but more slowly. The gravitational interaction between Jupiter and Saturn reversed both planets' migration, sending them back outward to approximately their current orbits. This tack, the reversal from inward to outward migration, had enormous consequences for the inner solar system. As Jupiter moved inward, its gravity scattered and destroyed many of the planetesimals and protoplanets in the inner disk, effectively clearing out material. As it moved back outward, it allowed a reduced amount of material to reaccumulate, leading to the formation of the relatively small terrestrial planets we see today: Mercury, Venus, Earth, and Mars. Without the Grand Tack, the inner solar system might have contained several super-Earths, planets significantly larger than Earth, which is actually the most common configuration found in exoplanet systems around other stars. The fact that our solar system lacks super-Earths may be directly attributable to Jupiter's early gravitational housekeeping. Even more critically, Jupiter's migration may have been responsible for delivering water to Earth. The region of the protoplanetary disk where Earth formed was probably too hot for water ice to exist as a solid, meaning the raw materials that built Earth were likely dry. Water had to be delivered from farther out in the solar system, beyond the so-called snow line, the distance from the Sun beyond which temperatures are low enough for water to freeze into ice. The snow line in our early solar system was located at roughly 2.5 to 3 astronomical units from the Sun. Jupiter's migration, both inward and outward, would have gravitationally scattered water-rich asteroids and comets from beyond the snow line into the inner solar system, where some of them collided with the young Earth and delivered the water that now fills our oceans. Studies of the isotopic composition of Earth's ocean water, specifically the ratio of deuterium to hydrogen, show a close match to the water found in certain types of carbonaceous chondrite meteorites, which originated in the outer asteroid belt near the snow line. This is strong evidence that Earth's water was indeed delivered from the outer solar system, and Jupiter's gravitational influence was almost certainly a major driver of that delivery process. So when we ask the question, would life exist on Earth without Jupiter? The answer is genuinely unclear, but probably leans toward no, not because Jupiter simply blocked asteroids, but because Jupiter fundamentally shaped the conditions that made Earth habitable in the first place. It influenced the size of Earth, the amount of water Earth received, the stability of Earth's orbit, and the long-term frequency of catastrophic impacts. Remove Jupiter from the equation, and you get a completely different solar system, one that might have super-Earths. or might have dry inner planets, or might have a chaotically unstable configuration where no planet maintains a stable climate long enough for complex life to evolve. Jupiter is not just a shield, it is an architect. Now let us turn to Jupiter's extraordinary system of moons, because this is where the search for extraterrestrial life in our solar system becomes most compelling. Jupiter has at least 95 confirmed moons as of the most recent surveys, making it the planet with the most known natural satellites in our solar system, recently surpassing Saturn. The vast majority of these are small, irregular moons, captured asteroids and comets ranging from less than a mile to a few tens of miles in diameter, that orbit Jupiter at great distances in inclined and often retrograde orbits. But the four large moons discovered by Galileo Galilei in January 1610, Io, Europa, Ganymede, and Callisto, are worlds unto themselves, each with unique characteristics that make them among the most scientifically interesting objects in the entire solar system. Io, the innermost of the four Galilean moons, orbits Jupiter at an average distance of about 262,000 miles, just slightly farther than the moon is from Earth. It has a diameter of approximately 2,264 miles, making it slightly larger than Earth's moon. Despite its modest size, Io is the most volcanically active body in the solar system. And it is not even close. Io's surface is covered with hundreds of active volcanoes, lava flows, and volcanic calderas. Some of its volcanic plumes extend more than 300 miles above the surface, launching sulfur and sulfur dioxide gas into space. The surface is constantly being resurfaced by fresh lava flows, which is why Io has almost no impact craters. They get buried as fast as they form. The colors of Io's surface range from bright yellow and orange to dark red and black, all due to various allotropes and compounds of sulfur deposited by volcanic activity. The source of all this volcanic energy is tidal heating. Io is locked in an orbital resonance with Europa and Ganymede. For every 4 orbits Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly 1. This resonance forces Io's orbit to remain slightly elliptical rather than perfectly circular, which means the tidal forces exerted by Jupiter's enormous gravity vary as Io moves closer and farther from Jupiter on each orbit. This constant tidal flexing generates friction inside Io, which produces enormous amounts of heat, estimated at roughly 100 trillion watts, or about 100 terawatts, which is roughly 5 times humanity's total power consumption. This heat melts rock inside Io and drives the relentless volcanic activity that defines the moons. Character. Europa, the next moon out, is the one that planetary scientists get most excited about, and for very good reason. Europa has a diameter of approximately 1,940 miles, slightly smaller than Earth's moon, and its surface is covered with a shell of water ice that is remarkably smooth and young. Europa has fewer impact craters than almost any other solid body in the solar system, indicating that the surface is geologically young, probably no more than 40 to 90 million years old, and is constantly being renewed. The surface is crisscrossed by an intricate network of reddish-brown lines called lineae, which are thought to be cracks in the ice shell that have been filled with material from below. And what lies below is the main attraction, a global ocean of liquid salt water, estimated to be 40 to 100 miles deep, containing roughly 2 to 3 times the volume of all of Earth's oceans combined. The evidence for this ocean comes from multiple sources. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, detected perturbations in Jupiter's magnetic field as it passed near Europa that were consistent with an electrically conducting layer, salt water, beneath the ice. Subsequent analysis of Europa's slight gravitational deviations from a perfect sphere confirmed the presence of a dense liquid layer, and observations from the Hubble Space Telescope in 2012 and 2014 detected what appeared to be plumes of water vapor erupting from Europa's south polar region, reaching heights of about 125 miles above the surface before falling back, direct evidence that the ocean can breach the ice shell and vent into space. The reason Europa's ocean is so exciting for the search for life is that it potentially has all 3 ingredients that astrobiologists consider necessary for life as we know it: liquid water, a source of chemical energy, and the right chemical building blocks. The ocean provides the water. The tidal heating of Europa's rocky interior, driven by the same orbital resonance mechanism that heats Io, though at lower intensity, could drive hydrothermal vents on the ocean floor. Similar to the deep-sea hydrothermal vents on Earth that support thriving ecosystems of chemosynthetic organisms entirely independent of sunlight. The chemical building blocks, carbon, nitrogen, sulfur, phosphorus, could be present in Europa's rocky mantle and delivered to the ocean through hydrothermal circulation. On Earth, hydrothermal vents on the ocean floor support entire ecosystems of bacteria, tube worms, shrimp, and other organisms that derive energy not from the sun, but from chemical reactions between seawater and hot rock. If similar conditions exist at the bottom of Europa's ocean, then microbial life, or something analogous to it, could potentially exist there right now. NASA's Europa Clipper mission, which launched successfully on October 14, 2024, aboard a SpaceX Falcon Heavy rocket, is designed to investigate exactly these questions. Europa Clipper is scheduled to arrive at Jupiter around April 2030, where it will enter orbit around Jupiter and perform approximately 49 close flybys of Europa over the course of its primary mission. The spacecraft carries a suite of 9 scientific instruments, including ice-penetrating radar that can probe the thickness of Europa's ice shell and potentially detect the ocean directly, a mass spectrometer that can analyze the composition of any plume material the spacecraft flies through, and cameras and spectrometers that will map the surface in unprecedented detail. Europa Clipper will not search for life directly. It does not carry a life detection instrument, but it will determine whether Europa's ocean has the conditions necessary to support life, effectively laying the groundwork for a future lander mission that could directly sample Europa's surface, or even drill through the ice to reach the ocean below. Ganymede, the third Galilean moon in order from Jupiter, is the largest moon in the entire solar system. With a diameter of approximately 270 miles, Ganymede is larger than the planet Mercury, which has a diameter of approximately 3,032 miles. If Ganymede orbited the Sun instead of Jupiter, it would likely be classified as a planet in its own right. Ganymede is composed of roughly equal amounts of rock and water ice, and its surface displays 2 distinct types of terrain: dark, heavily cratered regions that are very old, and lighter, grooved regions that are younger and show evidence of tectonic activity. Like Europa, Ganymede is believed to harbor a subsurface ocean. Though Ganymede's ocean is thought to be sandwiched between layers of ice, a high-pressure ice layer below and the outer ice shell above, rather than being in contact with a rocky seafloor as Europa's ocean may be. This ice sandwich makes Ganymede's ocean somewhat less promising for life than Europa's, because direct contact between water and rock is thought to be important for generating the chemical energy that life needs. However, Ganymede has another distinction that makes it unique among all moons in the solar system. It has its own internally generated magnetic field. Ganymede is the only moon known to possess a magnetic field driven by a dynamo in its metallic core, similar to Earth's magnetic field. The Galileo spacecraft detected this magnetic field in 1996. And subsequent observations confirm that it creates a small magnetosphere around Ganymede that is embedded within Jupiter's much larger magnetosphere. The existence of this magnetic field tells us that Ganymede's iron-rich core is at least partially liquid and convecting, generating electric currents through the dynamo mechanism. Ganymede is, in many respects, more like a small planet than a typical moon. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, which launched on April 14, 2023, is primarily focused on Ganymede. JUICE is scheduled to arrive at Jupiter in July 2031, where it will spend several years studying Jupiter, Europa, and Callisto through a series of flybys before entering orbit around Ganymede in December 2034, becoming the first spacecraft ever to orbit a moon other than Earth's. JUICE will study Ganymede's magnetic field, its subsurface ocean, its ice shell, and its tenuous atmosphere in detail, helping scientists understand how a moon can generate its own magnetic field and whether Ganymede's ocean could, despite its ice-sandwich configuration, have any potential for habitability. Callisto, the outermost Galilean moon, orbits Jupiter at about 1.17 million miles, far enough that it is outside the worst of Jupiter's intense radiation belts. Callisto has a diameter of approximately 2,996 miles, making it nearly as large as Mercury. Its surface is the most heavily cratered in the solar system, a testament to billions of years of impacts without significant geological resurfacing. Unlike Io, Europa, and Ganymede, Callisto is not in the orbital resonance that drives tidal heating, so its interior is cold and geologically quiet. However, even Callisto may harbor a subsurface ocean. The Galileo spacecraft detected subtle magnetic field perturbations near Callisto that are best explained by the presence of a conducting liquid layer, probably a thin ocean of salty water, at a depth of roughly 60 to 100 miles below the surface. This ocean, if it exists, is probably not a very hospitable environment for life due to the lack of internal heat sources, but its mere existence would demonstrate that subsurface oceans are common among large icy moons, which has profound implications for the potential prevalence of habitable environments in the outer solar system and beyond. Callisto's relatively benign radiation environment also makes it an attractive candidate for a future human outpost, a base from which astronauts could explore the Jupiter system without being constantly bombarded by the intense radiation that pervades the inner magnetosphere near Io and Europa. Together, the Galilean moons form what is essentially a miniature solar system orbiting Jupiter, complete with a volcanic inferno, Io, an ocean world that may harbor life, Europa, a planet-sized moon with its own magnetic field, Ganymede, and an ancient, cratered body that might nonetheless conceal a hidden ocean, Callisto. When Galileo Galilei first spotted these four moons through his telescope in January 1610, he recognized that they orbited Jupiter just as the planets orbit the Sun. And this observation was one of the key pieces of evidence that helped overthrow the geocentric model of the universe. More than 4 centuries later, we are still discovering new things about these moons. And the missions currently on their way to Jupiter, Europa Clipper and JUICE, promise to reveal whether the oceans beneath these icy surfaces could be home to living organisms. If life is found in the ocean of Europa or Ganymede, it would be the most significant scientific discovery in human history, proof that life is not a unique fluke confined to Earth, but a natural consequence of the right conditions, potentially common throughout the universe. Let us now address Jupiter's magnetic field in more detail, because it is one of the most extreme physical phenomena associated with any planet, and it has direct implications for the habitability of Jupiter's moons and the feasibility of future exploration. Jupiter's magnetic field is generated by the same basic mechanism as Earth's, a dynamo driven by the convective motion of electrically conducting fluid in the planet's interior, but the scale is incomparably larger. On Earth, the conducting fluid is liquid iron in the outer core. On Jupiter, it is metallic hydrogen, and there is vastly more of it. The resulting magnetic field is approximately 20,000 times stronger than Earth's in terms of its magnetic dipole moment. At Jupiter's cloud tops near the equator, the magnetic field strength is roughly 4.2 Gauss, about 10 to 20 times stronger than Earth's surface field. But near the poles and in certain anomalous regions, the field strength can be much higher. Juno's magnetometer measurements revealed that Jupiter's magnetic field is far more complex and asymmetric than expected. In the northern hemisphere, the field has multiple intense spots of concentrated magnetic flux, while the southern hemisphere has a more uniform, dipolar structure. One particularly striking feature is what scientists have nicknamed the Great Blue Spot, a concentrated patch of intense magnetic field located near Jupiter's equator in the northern hemisphere, where the magnetic field is locally very strong and directed inward, opposite to the overall direction of the field in that region. This magnetic anomaly has no counterpart on Earth or any other planet and suggests that the dynamics of metallic hydrogen convection deep inside Jupiter are more complex than simple models predict. Jupiter's magnetic field creates a magnetosphere, the bubble of magnetic influence that deflects the solar wind around the planet. That is the largest coherent structure in the solar system apart from the solar wind itself. Jupiter's magnetosphere extends approximately 1.8 to 4.5 million miles sunward from the planet, depending on solar wind conditions, and stretches at least 400 million miles in the anti-sunward direction, far enough to reach Saturn's orbit. If Jupiter's magnetosphere were visible to the naked eye, it would appear roughly 5 times the diameter of the full moon as seen from Earth, making it the largest single object in our night sky. Within this vast magnetosphere, charged particles, electrons, protons, and heavy ions from Io's volcanic emissions are trapped and accelerated to enormous energies, creating radiation belts that are millions of times more intense than Earth's Van Allen belts. The radiation near Jupiter is so intense that it can deliver a lethal dose to an unshielded human in minutes. This radiation is one of the primary engineering challenges for any mission to Jupiter's inner moons, particularly Europa, which orbits within the most intense radiation zone. The Juno spacecraft was designed with a titanium radiation vault weighing approximately 400 pounds to protect its sensitive electronics. And even so, the cumulative radiation exposure has been a constant concern throughout the mission. Jupiter also produces the most powerful auroras in the solar system. Unlike Earth's auroras, which are primarily driven by interactions between the solar wind and Earth's magnetic field, Jupiter's auroras are largely powered by the planet's own rapid rotation and the volcanic output of Io. As Io's volcanoes spew sulfur and oxygen into space, these atoms become ionized and trapped in Jupiter's magnetic field, forming a donut-shaped torus of plasma that encircles Jupiter along Io's orbital path. Jupiter's rapid rotation, remember, a full day on Jupiter is less than 10 hours, drags this plasma along with the magnetic field, accelerating it to enormous speeds. When these high-energy particles slam into Jupiter's upper atmosphere near the poles, they excite atmospheric molecules and produce auroras that emit primarily in ultraviolet and X-ray wavelengths, making them largely invisible to the human eye but spectacularly bright when viewed by UV and X-ray telescopes. Juno's ultraviolet spectrograph has captured stunning images of these auroras, revealing intricate curtains and arcs of light that dwarf anything seen on Earth. The power output of Jupiter's auroras is estimated at roughly 100 times greater than Earth's, and they are essentially permanent. Jupiter's auroras never stop, because the supply of plasma from Io and the planet's rotation are continuous. One of the most intriguing discoveries from Juno is that Jupiter's magnetic field is not static but is changing over time. By comparing Juno's measurements with those taken by earlier spacecraft, Pioneer 10 and 11 in the 1970s, Voyager 1 and 2 in 1979, and the Galileo orbiter from 1995 to 2003, scientists determined that the Great Blue Spot and other magnetic features are slowly drifting, indicating that the deep metallic hydrogen currents responsible for generating the field are themselves evolving on timescales of decades. This is analogous to the secular variation of Earth's magnetic field, which drifts and occasionally reverses on timescales of thousands to millions of years. But observing it on Jupiter provides a window into the dynamics of an entirely different type of planetary interior. Finally, let us confront what may be the most mind-bending fact about Jupiter. It very nearly became a star. Jupiter is composed of roughly 90% hydrogen and 10% helium by number of molecules, which is almost identical to the composition of the Sun and other stars. The difference between Jupiter and a star is not composition but mass. In order to ignite hydrogen fusion, the nuclear reaction that powers stars, the temperature and pressure at the core must reach approximately 18 million degrees Fahrenheit and millions of atmospheres. Jupiter's core temperature of roughly 43,000 degrees Fahrenheit is impressively hot, but falls far short of this threshold. To reach fusion conditions, Jupiter would need to be approximately 80 times more massive than it currently is, roughly 0.08 solar masses, which is the minimum mass for a hydrogen-fusing star, known as the hydrogen-burning limit. At masses between about 13 and 80 Jupiter masses, an object is classified as a brown dwarf, too massive to be a planet, too lightweight to be a true star. Brown dwarfs can fuse deuterium, a heavy isotope of hydrogen, in their cores, which produces some energy, but they cannot sustain the ordinary hydrogen fusion that powers main-sequence stars. Jupiter, at only 1 Jupiter mass, falls well below even the brown dwarf threshold. So while it is poetic and evocative to say that Jupiter is a failed star, the technical reality is that Jupiter would need to be roughly 80 times heavier to qualify as even the faintest, coolest type of red dwarf star. That is a big gap. However, the description is not entirely without merit, because Jupiter does share several important characteristics with stars and brown dwarfs that distinguish it from ordinary planets. First, as mentioned earlier, Jupiter radiates significantly more heat than it receives from the Sun, roughly 67% more. This internal heat comes from the slow gravitational contraction of the planet, a process called Kelvin-Helmholtz contraction, which is the same process that heated up the pre-stellar nebula before nuclear fusion ignited in the Sun's core. Jupiter is still slowly shrinking, by roughly 0.8 inches per year, according to some estimates, and this contraction converts gravitational potential energy into thermal energy. In this sense, Jupiter is powered by the same energy source that powers protostars. It simply never accumulated enough mass for fusion to take over. Second, Jupiter's composition. Internal structure, with a metallic hydrogen layer generating a magnetic dynamo, and atmospheric chemistry are all more reminiscent of a low-mass stellar object than of a rocky planet. And third, if you look at the population of known exoplanets, there is a continuous spectrum of objects from terrestrial planets through super-Earths, ice giants, gas giants, brown dwarfs, and low-mass stars, with no sharp dividing line between the categories. Jupiter sits on this continuum in an interesting position, clearly a planet, but one with distinctly stellar affinities. Had the solar nebula contained just a few times more mass in Jupiter's feeding zone, or had the timing of gas accretion been slightly different, it is conceivable that Jupiter could have accumulated enough material to become a brown dwarf, or even a very low-mass star. In that scenario, our solar system would have been a binary star system, two suns in the sky, though the second sun would have been a dim, cool, reddish object far less luminous than the Sun. The effects on Earth would have been dramatic and probably catastrophic. A stellar-mass Jupiter would have destabilized the orbits of the inner planets, potentially ejecting some of them from the solar system entirely. The habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, would have been completely different and possibly non-existent in any stable configuration. Life as we know it would almost certainly not have arisen. So in a sense, the fact that Jupiter failed to become a star is one of the luckiest breaks in the history of our solar system. Jupiter is massive enough to have shaped the solar system's architecture and protected Earth from excessive bombardment, but not so massive that it became a luminous body that would have made Earth's orbit unstable. It occupies a gravitational sweet spot that has been essential for the development of a stable, habitable environment on our planet. If you step back and consider everything we have covered, Jupiter's role as gravitational architect, cosmic shield, and failed star, its impossible internal physics, its centuries-old storms, its moons with hidden oceans that might harbor life, its magnetic field that dwarfs anything else in the solar system, a coherent picture emerges. Jupiter is not simply the largest planet orbiting the Sun. It is the keystone of our solar system. Remove it, and the entire structure changes. The inner planets might not exist in their current form. Earth might not have water. The bombardment rate might be different, higher or lower depending on the details, but certainly different. The moons with their tantalizing oceans would never have formed. The great storms, the metallic hydrogen, the auroras, the magnetic field, all of it would be gone. And with it, quite possibly us. We owe our existence, at least in part, to a ball of hydrogen and helium 484 million miles away that spins once every 10 hours, radiates more heat than it receives, crackles with lightning bolts hundreds of times more powerful than anything on Earth, and harbors worlds beneath its moon's icy surfaces that might, just might, contain the second example of life in our solar system. The next decade of space exploration, with Europa Clipper approaching Jupiter and JUICE following close behind, will begin to answer the question that Jupiter has posed since Galileo first turned his telescope skyward. What secrets are you hiding? And if those missions discover evidence of life in the oceans of Europa or Ganymede, it will confirm what Jupiter's story has been suggesting all along, that this planet, more than any other in our solar system, holds the key to understanding not just where we came from, but whether we are alone.